Thanks for the introduction. And so, yes, I'm Adrian JACKSON. I'm from EPCC at the University of Edinburgh, and I'm going to talk about some of the work we've done in the HPC wind energy project on looking at some of the optimizing applications, optimizing performance for applications that are being used inside in the project. So it's going to be a little bit different, I think, from most of the talks today and in the rest of the workshop, in that I'm not really talking about wind energy particularly. I'm talking about how we get the applications you're using to do simulations for wind energy to run faster or more efficiently. And actually this work that I'm presenting today, I talked about at the workshop last year as well, but we've done some more work on that, so we're updating on where we are now. But the nice thing is that some of the things that we can do in the underlying optimization of applications can be more widely applicable to a whole range of applications. So we have the potential to do work on one or two applications, but sort of demonstrate what's possible for a whole range of different applications. And of course, it means hopefully that you get your results quicker, or you get your results more efficient. You're able to calculate your results more efficiently, which at the end of the day means more science for less money. That's what we're trying to do here. And I have other colleagues here at Edinburgh EPCC who are also working on the project, doing other kinds of optimization. I was focusing on a particular kind of optimization, which was how do we improve the I/O performance, so reading and writing data on applications, so that's not a bottleneck, and so that's not costing too much and slowing the applications down. And actually, the work that we did here came out of a previous European-funded research project, where we were looking at how you could use new memory technologies to improve high-performance computation and data analytics and machine learning, particularly looking at what's happening with memory technologies across a range of applications. And what we see nowadays is actually that memory technologies for high-performance computing are becoming more varied and more specialized for different applications. Particularly, we now see high bandwidth on processor memory, what's often called HBM or HBM2, which provides very large bandwidth for fast local memory on processors. And an example of this could be a GPU. So some of the latest GPUs have this high bandwidth memory on them to give them great performance. Or the A64FX processor from Fujitsu, which also has this. It has 32 gigabytes of high bandwidth memory on the processor to give you improved performance and try and reduce that memory bottleneck that we have on computational systems these days. Obviously, we've been working with main memory, or what we call DRAM, for a long time. And that's something that's required to store your data and allow you to update and modify your data as your applications going on. And high bandwidth memory is just a version of DRAM, but it's a version of DRAM which has been sped up and put on the processor itself. And then we're also seeing this other forms of memory coming in at the other end of the spectrum, which are slower but much larger and can store data long term. And they're what we call byte addressable persistent memory. Other people also call it storage class memory or non-volatile memory, or NVDIMMs. And the idea here is that it's very high capacity. So on the A64FX with this high bandwidth memory, for instance, your processor, you've only got access to 32 gigabytes of memory, whereas this byte addressable persistent memory, particularly the version from Intel, which is on the market at the moment, the Optane memory, each DIMM can be up to 512 gigabytes, and inside a single node you can get up to 6 terabytes of memory. So it's much larger capacity. It stores its data long term, so you can leave data there and come back to it even through power cycles. That's what's the persistent part of it. And it also is pretty low energy when you're not using it. So if you're not reading and writing data from it, it doesn't consume large amounts of energy. Actually, if you try and write data to it, it's pretty high energy, but reading data from it is lower energy, and not using it at all is very low energy. And this is important because, you know, DRAM memory is quite a high consumer of energy inside a computer system. You know, something like 40–50% of your energy could be being consumed by your RAM, depending how much RAM you've got and what other things you have in the node. But that means that we're moving from this scenario of, whereas in the past we had very simple memory hierarchies for applications. So on your processor, you had a cache or number of level cache, and then you had main memory, and then you have storage, which is things like parallel file systems, tape stores, those kind of things. Actually, at the moment now, we're moving into a scenario where we have the potential for really quite complex memory hierarchies, something like a processor with cache and also high bandwidth memory on the processor, and some main memory, and potentially some of this non-volatile memory and storage in the future. Further out, sort of slower, faster storage. Or potentially we could be converging on a scenario if these memory technologies turn out to be useful and cost effective, and you can easily exploit them for your applications, where we could sort of collapse this down into something much simpler, where we had cache and then high bandwidth memory on the processor, get rid of the DRAM altogether, and then have some of this byte addressable storage to give us a larger capacity. And potentially, actually, and this is what we looked at quite strongly in our previous project, this Next Gen IO project, could you get rid of the external storage altogether as well? So get rid of our Lustre file systems, get rid of our parallel file systems, tape stores, that kind of thing, because we have this very large memory inside the computer nodes, and that very large memory can keep the data long term, so it can act as a persistent store. But this, of course, is not without challenges. As I've already mentioned, the kind of persistent memory we have available at the moment is this form of memory from Intel called Optane ECPMM. What's transformative from a memory point of view about it is that it comes as persistent memory, so you can store data long term, but it sits inside the same memory channels as your normal volatile memory. And that means you can access it in a in different ways than if you were to go out and write a file or read data from a file. You can access it as if it was just memory, and read and write chunks of data to it, just using standard programming techniques. And the nice thing about it is, from a performance point of view, it really has very high performance, at least if you compare it to parallel file systems. So we have access to a system which has got 34 nodes with this memory inside it. And when we go off and benchmark it, we can get up to 2 terabytes, actually slightly over 2 terabytes of read performance, and about 300 or 400 gigabytes a second of write performance to this storage, using only 32 or 34 nodes. And that's great if you compare it to the sort of performance of the fastest file systems in the world. It's very similar to the top systems out there in terms of read and write performance, but we're using a fraction of the resources here. We're using 32 compute nodes to hold all our full file system, whereas if you go and look at some of the big file systems that provide similar levels of performance, you'd be using 500, 1,000, 1,500 compute nodes to do that. So we can see that the underlying hardware has the potential to give great performance. The question is, how easy is it to use in applications, and how efficient is it? How expensive is it to use in systems in general? I should also point out that this is great for I/O performance. It's not so great for memory performance. So if we were to look at the high bandwidth memory, which is that other form of new memory that's coming out as well, where you put the memory directly on top of a processor to give you very fast local access to data, on something like the A64FX chip from Fujitsu, you can get about 800 gigabytes a second of read performance on a single processor there. And here we would take up to about 20 nodes to get the same kind of performance using this Optane memory. But then, of course, the Optane memory here is much larger. So orders of magnitude more data storage are available compared to the high bandwidth memory. So there's these kind of trade-offs when we look at sort of developing these kind of systems. So it's clear that this byte addressable persistent memory, this Optane memory, has the potential to really speed up I/O performance compared to traditional parallel file systems. One of the other interesting things about it, of course, is that because we're putting it directly into the compute nodes, you also have local access to storage. So these pictures are examples of this one here with the 256 processor graph. There's examples of us benchmarking the performance of I/O from an application over time. Same application, same data set. We just run it on a system, run it 5 times a day, every day for a month, and see how long the I/O takes. And in this scenario, we can see most of the time it takes 2 or 3 seconds to do the I/O per iteration for this given application. But sometimes it takes, it took over 30 seconds, and a reasonable amount of the time it takes up to 10 seconds to run. So you can see on our current systems, you often get some performance overheads and performance interference between your application and someone else's application when it's running on a shared resource like a parallel file system. And that's because other programs can be using that same parallel file system when you're using it, and they may be heavily using it, and then your performance goes down, or no one may be using it and your performance goes up. Of course, if you put the hardware, the storage directly into the compute nodes, then actually you're likely to have that I/O hardware dedicated to your application, so you shouldn't see this kind of variation. You shouldn't see this performance difference depending on what other people are doing on the system. So that's another of the features which makes it quite nice. But of course, on the flip side of that, that's going to be hard to use from a whole system point of view, because if you run your program and it writes some data out to the local storage, and then you want to run your program again and use that data, but it's sitting on compute nodes that are now being used by another application, by another person, that's not going to be convenient for you. So there's actually, well, there's some benefit of having the storage locally. There's some challenges to it as well, because you maybe need to move data in and out of that storage so that it can be used elsewhere, and make sure that the resources can be shared on a system, like most HPC systems, where individual users don't get much choice about where their jobs run, and nodes can be used for many jobs over time. And that's because effectively what you're doing if you put the storage in the node is you're moving from a scenario we have here, where we have all our compute nodes on a standard HPC system, and they're connected together by some kind of network, and then that network is connected to some kind of external file system. So if you run a job on this node up here, it can see all the data in the file system. And if you run a job on this node over here, it can see all the data in the file system. If you then move across to putting all the data inside the compute nodes, then of course each node is connected together. But if your job is running here and stores its data, and then you rerun the job over here, you're going to have some mechanism for moving the data across between the systems. And actually, given the nature of this memory and how expensive it may be, you may even end up with systems that look a little bit like this, where you don't have the storage in every node, but you have it in some nodes, and it's shared between the nodes, and you need some way of using that. So coming out of that previous Next-Gen I/O project, we have the system where we have large amounts of storage, actually 3 terabytes of this storage in the node. And we have 34 of these nodes, so we have about 100 terabytes of this storage, and an external Lustre file system. And we've done work in the past to see how we can utilize that to get good performance for applications. And one example of something we did in the past was some OpenFirm work, where we were looking at running OpenFirm simulations here, either using the external Lustre file system or writing and reading all our data locally on the in-node storage and then copying it back out to the Lustre file system at the end. So in this scenario, we're still using that external file system, but it's only ever used as a store before the job starts and a store after the job finishes. And all the stuff that's happening as the job's running goes to the local storage. When your job's finished, the data gets copied away and off we go. And here we extended the scheduling system, and we put in some middleware functionality to do this movement of data for you automatically, so you didn't have to do it yourself. So you just said, I want to run this job, these are the files it needs, and the system, when it scheduled your job, copied the files it needs onto the local storage. You run your job, and then you tell it what files you want to copy off at the end of the job, and it copies it back off, and then the next job runs. And in this example, we were running OpenFirm doing actually some aircraft simulation, but it could easily have been a wind turbine in here. A couple of different simulation setups. And of course, OpenFirm is not just one monolithic application. You have multiple steps here. So, you've got your data decomposition as well as your solver and potentially data analysis at the end of it. But clearly what we want to do for this kind of application is to do the decomposition on the same nodes that we're going to run the job on. So actually when we do the data decomposition, that sets up the data in the correct places on the in-node storage, and then we can run our jobs, and then we can go away and hopefully get some benefit out of that. And what we actually see here is this table slightly complicated, but what we can actually see here is that actually doing the decomposition for our large test case does improve performance a little bit on the using the local storage rather than reading and writing all our data from Lustre, but not a huge amount. But where we see the big difference is when we're running our solver, and we're running our solver here, and we're writing out quite a large amount of data. So actually what we're running here is outputting every iteration rather than every 10 iterations or every 100 iterations. But you can see here that we can get our solver to go nearly 10 times faster when we write to this local storage than we do when we write to external Lustre, because it's spending a lot of time doing the I/O. And that means that we can get rid of all that kind of overheads by using the fast local storage. Now, at the end, we still have to copy the data back out again, and that takes a bit of time. So it doesn't speed the whole thing up 100%. But actually, what we're doing here is we're running the solver for quite a short period of time just for our benchmarking. In reality, this solver will be running for a much longer set of iterations, and then that benefit would be much higher. And the nice thing about this is you could easily argue that in this scenario, the way we're running OpenFirm, we're doing more I/O than you would generally do. And then there's an interesting discussion to be had there is, are people only doing writing out of data every 10 iterations or 100 iterations or something like that because that's all the data they need and they don't care about the rest? Or are they doing that because actually if they write out too much, write out iteration every time step, data every time step, it just costs them too much in terms of I/O, and so they can't afford to do that. So here we're writing out every time step, every iteration, and it's very expensive going out to Lustre. But I don't have figures here, but in reality, if we did on the local storage, wrote out every iteration, every time step, our data that we want to visualize at the end, or every 10 iterations or every 100 iterations, it really has very, very little performance impact on the solver when we go into the local storage. So the solver, if we went out to Lustre and did no I/O at all, has very similar performance to this, where we're writing out every iteration, writing out as much data as we possibly can. And we are doing it to the node local storage. So the nice thing about that is that we can use this node local storage, this persistent memory, to actually start to pick up things that we wouldn't necessarily be able to do any other way, because it's just too expensive to do it if our IO is going further out. Now, whether you need that for your application or not is a different question, but there may be things you can do when you start to visualize data or analyze data when you've got the full output of your run, compared to if you're dropping out 9/10 of it and only taking every 10th data dump or something like that. And we're looking at the moment actually in some very large scale simulations of tidal turbines, actually, whether we can start to iterate dump our data every time step rather than every 10 time steps. And that would really require very, very large amounts of IO, but that maybe will let us do some analysis that we couldn't do otherwise. That was a previous project. That's not what we were doing here, particularly in HPC wind energy. What we were doing here was actually looking at a similar kind of use case, but an application called N3D. And N3D is a joint forward adjoint method where it uses a DNS approach to do the forward step. It collects all the data from that and then does an adjoint method on the full output of the DNS forward step at the end. And this means that it requires very large amounts of storage for even a small simulation. So if we look at our examples here, we're doing a medium simulation. You can scale up to, in terms of computationally, at most 72 processors. So, on a system like we're running here, a few tens of cores per node, you're using at most 2 or 3 nodes. But the actual intermediate data you need to store to go between this forward and adjoint method steps is 4 terabytes. So quite a large amount of data to write out on the forward step and then read back in on the adjoint step. If we go up to something a bit bigger for a more realistic simulation, we will be looking at something like 512 processors maximum. So you could use at most 512 cores to run this. That's the amount of computational domain you can decompose across. And that one there, that takes about 40 terabytes of storage to go between these things. And the way N3D generally works, it uses the file system to store this transitory data. The data that you don't need it ever at the end of a simulation, you just need it whilst the simulation is running to enable this forward and then adjoint approach. And so that clearly is quite a lot of IO overhead. So an example, particularly when we first started looking at this, what would happen is on that medium test case where you could go up to about 72 cores, it produced nearly 1 million files and 4.5 terabytes. On the larger case, you're up to 6.4 million files and 30 plus terabytes of data produced. And here's an example of these are the Lustre, so the file system logs on the right-hand side here, of us running this simulation out to the Lustre. And you can see here that for this forward phase, there's very high load on this external file system. And then we go through a phase where you're reading all that data back in, and then you go through a phase where actually it's just doing the adjoint method and there's hardly any IO going on here. So we can see that, particularly for this application, for this system, it's very much has a high bottleneck on transferring this data between the forward and adjoint phases. Now, we can move this instead to use the node's local storage. It doesn't require large amounts of re-engineering the application. Effectively, the way it's set up is it writes individual files out per process. So we just have to tell it where to write those files. Instead of writing them all out to a Lustre file system, we write them out to its node local storage. And we should be able to use that directly and bypass this IO bottleneck. We have to be a little bit careful, but because we now have this byte addressable persistent memory in the compute nodes, each node has 2 processors. They both have memory attached to them. We have to be careful that we follow these NUMA issues and don't get too bogged down in performance that way. So we have to make sure that each process knows where it's running. And it doesn't need huge amounts of work to do this, but you do have to do a little bit of this kind of code where you go and say, okay, what core am I running on? Where's my local storage, and move it on from that way. But the nice thing is, and I'm just wrapping up here, so we should finish with questions in a minute. The nice thing is here is that you can see that we can go from, on the medium test case, running on 3 nodes, it took us about nearly 10,000 seconds to run the simulation. And then when we go to the persistent memory, it goes down by about 15%. But for the large test case, where we go up to 22 nodes and we're writing out nearly 40 terabytes of data, it took about 80,000 seconds to run the simulation. And then writing out to a persistent memory, it takes about 9,000 seconds. So in reality, actually, we can scale up our test case, scale up the number of nodes you use, and we don't really go any slower. We get the same performance because we're adding in this local storage, and that gives us the improved performance. Now, you could easily ask, why is this approach taken at all? You know, it seems crazy to write the data out and then read it back in. That's insane. But really, it's done to save resources, because you could just do this all inside memory, inside normal DRAM, just spread out your work and then save that data in memory and use it in memory. But if you were to do that, then the medium case on a standard system would take you, instead of 3 nodes, you'd have to use 16 nodes. And on the large system, instead of 22 nodes, we'd have to use 160 nodes. So you could bypass this step where you're reading and writing data out to the external file system, but you just require many more computational resources to do it. And so because we can reduce the cost of doing that to a file system, that means we can get good performance without having to go up by an order of magnitude more compute resources to get this done. Now, I'm running out of time, but in reality, this is just the beginning, because you can also start to do your I/O in different ways. And actually, instead of writing it out as file, you can write it out as memory. And if you write it out as memory, you can get much better performance. Not when we look at the writing out big chunks of data, but it means you can start writing out small chunks of data with the same costs as if you were writing out large chunks of data. Because if you've done anything with I/O and HPC, you'll know that most of the time, parallel I/O, you need to do large chunks of data writing to get you good performance. Small chunks of data writing gives you terrible performance, and you really end up with a bottleneck. But the nice thing about this persistent memory is we can start scaling down and doing writes in very small chunks, 256 bytes, 512 bytes, and still get the same performance as if we were writing a megabyte or 10 megabytes at the same time. And that means that there is potential to start re-engineering applications to do much more small reads and writes, spread that out across the application and improve the performance. But I will stop there and happily take any questions if there are any. And if anyone is interested
Yes, thank you.
in this kind of work or playing around with this kind of hardware, do let me know, because we're keen to collaborate with people, and keen to give people access to the hardware to play with themselves as well if they're interested.